Weldon Word wasn't supposed to be building a guided bomb in the basement of Texas Instruments' Dallas facility in 1964. His job description said laser research, not weapons development. But every night on the news, he watched grainy footage from Vietnam, B-52s dropping strings of unguided bombs across jungle canopy, fighter bombers making repeated passes over bridges and supply depots, pilots getting shot down trying to hit targets that required dozens of missions to destroy. The math didn't work. The U.S. military was dropping more tonnage than in all of World War II. Yet bridges stood, supply lines flowed, and the body count climbed on both sides. Word had spent 3 years working with ruby lasers at Texas Instruments, understanding how coherent light could travel in tight beams over long distances. The principles seemed obvious to him. If you could paint a target with a laser beam, you could build a seeker head that would home in on the reflected light. Shine the laser at a bridge abutment, drop a bomb with the seeker attached. Let physics do the rest. No complicated inertial guidance systems, no radar emissions to give away your position, just a simple detector following reflected photons to the target. The problem was convincing anyone it mattered. The Air Force had spent 15 years developing sophisticated guided weapons, radio-controlled bombs from World War II, television-guided munitions in Korea, complex beam-riding systems that never quite worked in combat conditions. Each program cost millions, each promised revolution, and each ended up gathering dust in Nevada test ranges, while pilots went back to dropping dumb iron bombs the way their fathers had in 1944. Word's colleagues at TI told him the military wouldn't be interested in another guided bomb proposal. The Pentagon's Guided Weapons Office had heard it all before, so Word didn't ask for permission. He assembled a small team: Larry Erickson, a circuit designer who understood photodetectors, and a handful of technicians who could machine parts after hours. They worked in a basement lab that TI used for experimental projects, the kind of place where engineers tinkered with ideas that might become products in 5 years, or might become nothing at all. Word's boss knew what was happening, but didn't stop it. Texas Instruments had built its reputation on letting engineers follow interesting problems, and Word's laser-guided bomb qualified as interesting even if it seemed impractical. The first seeker head was laughably simple: a 4-quadrant photo detector mounted in a gimbal, connected to analog circuits that compared light intensity across the 4 sensors. When the laser spot moved right, the right sensors saw more light, generating a voltage differential that would eventually drive control fins. Word tested it by shining a laser pointer across the lab and watching the detector track the beam. It worked, sort of. The response time was slow, the sensitivity marginal, and the whole assembly weighed more than the guidance section of a Sidewinder air-to-air missile. But it tracked laser light reliably, and that was enough to move forward. By early 1965, Word had a prototype seeker, small enough to fit on a bomb nose. He'd requisitioned surplus M117 750-pound general-purpose bombs, the standard weapon hanging under every F-4 Phantom in Southeast Asia, and convinced TI's machine shop to fabricate adapter kits that could mount his seeker to the bomb's nose. The design used 4 movable canard fins near the front, rather than tail fins, giving faster response to guidance commands. It was crude engineering, but it was real hardware that could potentially fly. The Thanh Hoa Bridge sat 70 miles south of Hanoi, a 540-foot steel and concrete span carrying the main rail line between North Vietnam and China. American pilots called it the Dragon's Jaw. Between April 1965 and December 1972, the U.S. Air Force and Navy flew 873 sorties against that single bridge. They lost 11 aircraft to anti-aircraft fire and surface-to-air missiles defending the target. They expended hundreds of tons of ordnance: 500-pound bombs, 750-pound bombs, 2,000-pound bombs, even experimental TV-guided walleyes that slammed into the riverbank instead of the bridge deck. The bridge remained standing, trains kept rolling, and pilots kept dying. The problem wasn't courage or skill. F-105 Thunder Chief pilots were hitting the bridge. They could see their bombs impacting the structure from their cockpits as they pulled off target. But unguided bombs released from 15,000 feet experienced unpredictable ballistic trajectories affected by wind, air density, release velocity, and a dozen other variables that made precision impossible. A bomb released from high altitude to avoid anti-aircraft fire might land 300 feet from the aim point. To guarantee destruction, you needed multiple direct hits on the same structural element, and unguided bombs couldn't deliver that consistency, so the Air Force adapted by going lower. Rolling Thunder missions descended to 5,000 feet, then 3,000 feet, putting aircraft squarely in the envelope of 37 millimeters and 57 millimeter anti-aircraft guns. The North Vietnamese responded by concentrating their air defenses around critical targets. By 1967, Thanh Hoa Bridge was defended by more than 100 anti-aircraft guns and multiple SA-2 surface-to-air missile sites. Attacking it became a suicide mission with minimal chance of success. Pilots went because orders said go, knowing the odds were terrible. The strategic absurdity extended beyond bridges. North Vietnamese supply depots, power plants, and command centers all required multiple strikes to achieve damage that might be repaired within days. The Ho Chi Minh Trail, a network of jungle paths moving men and supplies south, absorbed thousands of bombing sorties with negligible effect. Pilots reported destroying the same truck parks and storage facilities week after week because photo reconnaissance couldn't confirm permanent destruction. Civilian analysts at the Pentagon started calculating cost-per-kill ratios that made no economic sense. An F-4 Phantom cost $2.4 million in 1965. Each combat mission burned fuel, expended munitions, and wore out airframes that required expensive depot-level maintenance. Losing one aircraft to destroy a bridge meant trading a sophisticated weapons platform worth more than the target itself. Losing 11 aircraft to fail to destroy a bridge was strategic insanity. Back in Washington, Defense Secretary Robert McNamara's systems analysts tried applying statistical models to bombing effectiveness. They calculated circular error probable, the radius within which 50% of bombs landed, and discovered that unguided bombs from tactical altitudes had CEPs measured in hundreds of feet. To achieve 90% probability of destroying a hardened target, you needed dozens of sorties, and each sortie risked aircraft and pilots. McNamara's people recommended either accepting higher loss rates by bombing from lower altitudes or accepting that most targets couldn't be effectively destroyed with available weapons. Neither option was politically acceptable. The Air Force's Eglin Test Center had been evaluating guided weapons since the 1950s. But everything tested failed basic operational requirements. Radio-controlled bombs required the controlling aircraft to remain over the target, exposing it to defensive fire. TV-guided weapons worked only in perfect visibility and couldn't track through smoke or clouds. Radar-guided systems couldn't distinguish small targets from ground clutter. By 1965, the Guided Weapons Office had effectively given up on tactical precision munitions. Word needed to prove the concept worked outside his laboratory, so he took his prototype home. His garage in suburban Dallas became an improvised test range during the summer of 1965. He mounted the seeker head on a wooden frame, positioned it at one end of his driveway, and set up a helium neon laser at the other end, about 50 feet of separation. His teenage son aimed the laser at a whiteboard, while Word watched oscilloscope traces showing voltage outputs from the 4-quadrant photo detector. When the laser spot moved up, the top sensors registered higher voltage. When it moved left, the left sensors dominated. The differential signals were clean, predictable, strong enough to drive actuators that would move control fins. The real test came at a TI facility outside Dallas where they could actually drop things. Word's team built a test rig, essentially a bomb-shaped weight with the seeker head mounted on the nose and small compressed air thrusters replacing control fins. They suspended it from cables in a high bay warehouse, shined a laser at different points on the far wall, and measured how accurately the seeker tracked the moving laser spot. The response time was 40 milliseconds from laser movement to thruster activation. The tracking accuracy was within 2 degrees across a 20-degree field of view. Those numbers meant a bomb falling at 500 feet per second could make guidance corrections fast enough to actually hit what the laser was illuminating. Word wrote up the results in a technical proposal, 22 pages describing the seeker design, the expected guidance performance, and cost estimates for developing operational weapons. He titled it Laser-Guided Bomb Feasibility Study and submitted it through TI's Government Contracts Office to the Air Force's Guided Weapons Division at Eglin Air Force Base in Florida. The proposal requested $99,000 to build 3 operational prototypes and conduct live drop tests. For comparison, a single F-4 Phantom carried a sticker price 24 times higher. Eglin's response came back in 6 weeks. Not interested. The rejection letter cited concerns about laser propagation through atmospheric conditions, vulnerability to countermeasures, limited field of view, and unproven seeker reliability. But Word suspected the real reason was institutional fatigue. The Air Force had funded dozens of guided weapons programs since 1950. Most failed in testing. The few that reached production, like the GAM-83 Bullpup radio-controlled bomb, proved too complex for combat operations. Pilots didn't want complicated weapons that required special training and extra equipment. They wanted bombs that worked when you dropped them. And Word's laser-guided system required someone to shine a laser at the target throughout the bomb's entire flight time. Word persisted anyway. He took the rejection letter to TI's executive vice president and argued that laser-guided weapons represented a fundamental breakthrough, regardless of what the Air Force thought. TI's business strategy relied on developing technologies before customers realized they needed them. The company had built its reputation on transistors, integrated circuits, and infrared sensors, products that didn't exist until TI invented them. Word wanted TI to fund development internally, then demonstrate the technology to the military as a functioning system rather than a paper proposal. TI management agreed to limited funding, enough to build 3 complete bomb kits and conduct drop tests at a private range in New Mexico. Word's budget was $50,000, half what he'd requested from the Air Force, but it was enough. By October 1965, his team had fabricated seeker heads small enough to fit on standard 750-pound M117 bombs, designed canard fin assemblies that could be bolted to the bomb nose, and assembled analog guidance computers that would convert photo detector signals into fin commands. The hardware was ready. Now they needed to drop it and see if physics matched theory. The first live drop happened on a cloudless New Mexico morning in December 1965. TI had rented time on a private test range near Alamogordo, the same desert where the first atomic bomb had detonated 20 years earlier. Word's team chartered a twin-engine Beechcraft Baron, removed the right-side passenger door, and rigged a bomb rack underneath the fuselage. The plan was straightforward. Fly at 10,000 feet, illuminate a plywood target board with a handheld laser designator from a ground vehicle, release the bomb, and see where it hit. Word expected the bomb to land somewhere in the same county as the target. What happened exceeded every prediction. The bomb impacted 11 feet from the laser spot. Word thought the measurement was wrong. They'd painted the target board white, with a red circle marking the aim point, and the bomb crater was close enough that fragments had shredded the plywood. Word paced off the distance 3 times while his team photographed the impact site from multiple angles. 11 feet. From 10,000 feet altitude, after falling for nearly 40 seconds, through crosswinds that were gusting to 15 knots, the bomb had guided itself to within 11 feet of a laser dot the size of a dinner plate. They dropped 2 more bombs that afternoon. One hit 8 feet from the aim point. The other hit 14 feet away. But post-flight analysis showed the laser designator operator had jerked the beam during the terminal phase. The bomb had followed the laser movement precisely, which meant the tracking system was working even better than designed. Word's team returned to Dallas with 16mm film footage showing bombs curving through the air, tiny canard fins visibly adjusting as the seeker head tracked the laser spot. It was the most dramatic engineering validation any of them had witnessed. Word sent the test results to Eglin with renewed confidence. The data spoke for itself. Laser-guided bombs worked. They were accurate beyond any existing guided weapon. And they used proven components assembled into a system simple enough to manufacture in quantity. The second rejection arrived faster than the first. The Air Force acknowledged the test results, but questioned operational practicality. Who would designate targets during combat missions? How would you coordinate between the bombing aircraft and the designator? What happened if clouds blocked the laser beam? And most fundamentally, why did the Air Force need precision weapons when area bombing was already achieving strategic objectives? That last question revealed the real problem. The Air Force's bombing doctrine had evolved from World War II experience, where success meant putting maximum tonnage on target areas regardless of precision. Strategic Air Command measured effectiveness in megatons delivered. Tactical Air Command counted sorties flown and ordnance expended. Precision wasn't a metric that appeared in operational reports. Wing commanders got promoted for flying more missions, not for achieving better accuracy per mission. Word's laser-guided bomb threatened to upset a system where success was measured by effort expended rather than results achieved. Word found an unexpected ally in Colonel Joseph Davis, who ran Eglin's Armament Development Division. Davis had flown F-105s over North Vietnam in 1965 and watched friends die attacking targets that remained intact after dozens of sorties. He understood that unguided bombs weren't working, regardless of what the doctrine manuals said. Davis couldn't authorize procurement funding, but he could authorize testing funds, money designated for evaluating new technologies before they reached formal development programs. In March 1966, Davis allocated $100,000 for the Air Force to conduct independent drop tests of Word's laser-guided bomb. It was a bureaucratic end run around the procurement office's rejection, and it gave Word 6 months to prove his system worked well enough to force a policy change. By early 1968, the Air Force had conducted enough successful drop tests to authorize limited combat evaluation, but there was no infrastructure for actually using laser-guided bombs in Vietnam. The standard M117 bombs were already there. Every forward operating base had stockpiles of them. But Word's guidance kits weren't in production, and no aircraft had laser designators installed. The solution was Combat Hornet, a rushed field modification program that took existing technology and jury-rigged it into combat-capable systems. Texas Instruments delivered 124 guidance kits designated Paveway Jarn, each consisting of a seeker head, 4 canard fins, and the analog control computer. The kits weighed 50 pounds and could be bolted to 750-pound M117 bombs or 2,000-pound M118 bombs using standard explosive ordnance tools available at any airbase. An experienced munitions crew could convert a dumb bomb to a laser-guided weapon in 45 minutes. The real challenge was the laser designator. The Air Force adapted the AN/AVQ-10 pave knife pod, originally designed for a different guided weapon program that had been canceled. The pod contained a neodymium-doped yttrium aluminum garnet laser, NGAMIAG, in laboratory shorthand, producing a 1.064 micrometer wavelength invisible to human eyes, but perfectly matched to Word's seeker head sensitivity. The laser output was 10 watts pulsed at 10 pulses per second, creating laser spots on the ground, bright enough for the seeker to track from 15,000 feet altitude. The pod also included a low-light television camera so the operator could identify targets, and stabilization gyros to keep the laser beam steady despite aircraft turbulence. F-4 Phantoms received the pave knife pods mounted on underwing pylons. The system required 2 aircraft working together, one carrying the laser-guided bombs, the other carrying the designator pod. The designator aircraft would fly in a slow circle around the target at 15,000 feet, keeping the laser pointed at the aim point while the bomber released its weapons from a separate approach angle. The weapons systems officer in the back seat of the designator aircraft controlled the laser, steering the beam with a hand controller while watching the TV display. It was workable, but clumsy, requiring radio coordination and precise timing to ensure the bombs were actually tracking laser energy during their flight. The first combat mission happened on May 8, 1968, against a truck depot near the demilitarized zone. 2 F-4s from the 8th Tactical Fighter Wing launched from Ubon Royal Thai Air Force Base at dawn. The designator aircraft carried the Pave knife pod and no bombs. The bomber carried 4 Paveway bomber kits mounted on M117 bombs. They flew north for 40 minutes, approaching the target from different directions to confuse anti-aircraft gunners. At 14,000 feet, the weapons systems officer in the designator aircraft locked the laser onto a storage building while the bomber pilot rolled in on a standard dive bombing run. The first bomb guided perfectly, impacting the building's center. The second bomb hit 20 feet away, close enough that the combined explosions collapsed the entire structure. The third bomb walked the laser spot to a second building and destroyed it with a direct hit. The fourth bomb malfunctioned, the seeker head failed to track, and the bomb fell ballistically, impacting 200 feet from the target. But 3 hits out of 4 bombs was revolutionary accuracy by any standard. The mission commander's after-action report noted that the same target would have required 12 to 16 unguided bombs with multiple aircraft sorties, significant exposure time to ground fire, and no guarantee of success. Word got a copy of the combat report at TI headquarters 2 days later. He'd spent 4 years developing the technology, fighting Pentagon skepticism, and refining hardware through dozens of test drops. Now it worked in combat, and the evidence was photographic reconnaissance imagery showing smoking craters exactly where bombs were supposed to hit. The Dragon's Jaw had survived everything the Air Force threw at it for 7 years. Thanh Hoa Bridge had become a symbol of American bombing futility. 873 sorties, 11 aircraft lost, thousands of tons of bombs expended, and the steel spans still carried trains across the Songma River. Pilots who flew missions against it knew the odds. You went because orders said go. You dropped your bombs. You dodged flak and missiles on egress. And you watched reconnaissance photos the next day showing the bridge still standing. It was strategically worthless to keep attacking and politically impossible to stop. Operation Linebacker changed everything. In May 1972, President Nixon authorized unrestricted bombing of military targets throughout North Vietnam, lifting the gradual escalation constraints that had governed Rolling Thunder missions from 1965 to 1968. The Air Force planned a maximum effort strike against Thanh Hoa Bridge using every precision weapon available. Paveway laser-guided bombs had proven themselves in hundreds of combat missions by this point, achieving accuracy that made single-pass target destruction possible against structures that previously required weeks of sustained bombing. The mission launched on May 13, 1972. 14 F-4 Phantoms from the 8th Tactical Fighter Wing carried 24 Paveway 2 laser-guided bombs, an improved version of Word's original design with better seeker sensitivity and longer canard fins for increased maneuverability. The bombs were 2,000-pound M118 general-purpose weapons, large enough to destroy reinforced concrete structures with direct hits. Support aircraft included F-105 Wild Weasels to suppress surface-to-air missiles, F-ORs carrying conventional bombs to crater the approach roads, and EB-66 electronic warfare aircraft jamming North Vietnamese radar. The attacking aircraft approached from multiple directions at 15,000 feet, above the effective range of light anti-aircraft guns, but within engagement range of SA-2 missiles. 4 F-4s carrying Pave knife designator pods established orbits around the bridge, each pod operator locking his laser onto a different structural element: the western abutment, eastern abutment, center span support, and the roadway deck. The bomber aircraft released their Paveway weapons in coordinated sequences. ensuring continuous laser illumination as bombs fell for 40 seconds from release to impact. The first laser-guided bomb hit the western bridge abutment, creating a massive explosion that shook the entire structure. 3 more bombs walked across the span, each guided to a specific structural point. 2 bombs hit the center support pier simultaneously. The mission planners had timed releases to achieve near-simultaneous impacts, concentrating explosive energy on the same target element. The combined detonations severed the center span, dropping it into the Songma River. The eastern approach span collapsed next when 2 more bombs demolished its support pier. Within 13 minutes, the bridge that had survived 7 years of conventional bombing ceased to exist as a functional crossing. Post-strike reconnaissance showed what precision weapons could achieve. The bridge approaches were cratered by conventional bombs that prevented repair vehicles from reaching the wreckage. The center span was gone entirely. The western span had collapsed into the river. Even the abutments, massive concrete foundations designed to withstand artillery strikes, showed structural damage from direct hits by 2,000-pound warheads. The North Vietnamese made no attempt to rebuild. They constructed a pontoon bridge 2 miles downstream instead, tacit acknowledgement that the original bridge was beyond repair. Word watched gun camera footage at TI headquarters, grainy black and white film showing bombs tracking through the air, visible course corrections as canard fins responded to guidance commands, and the unmistakable geometry of weapons hitting exactly where lasers pointed them. The Dragon's jaw had finally fallen, not to greater tonnage or more sorties, but to precision that made every bomb count. 11 aircraft had been lost, failing to destroy this bridge with unguided weapons. 0 aircraft were lost, destroying it with laser-guided bombs. The math had changed completely. Word's original Paveway design was elegant, but primitive. Analog circuits comparing photodetector voltages and generating proportional control signals to move canard fins. The system worked, but its limitations became obvious once combat operations began in 1968. The 4-quadrant seeker had a narrow field of view, requiring the bomb to be released on a near-perfect trajectory toward the laser spot. If the bomber's aim was off by more than 15 degrees, the seeker couldn't acquire the laser, and the bomb fell ballistically. Cloud layers blocked laser energy, rendering the weapons useless during monsoon seasons, and the analog control system responded slowly to rapid target movements, causing misses when laser operators jerked the designator beam. Texas Instruments began developing Paveway 2 in 1970, redesigning every component based on combat feedback. The new seeker used a faster photodetector array with 60-degree field of view, 4 times wider than the original design. Bombs could now be released from steeper dive angles or greater off-axis positions and still acquire the laser spot during their descent. The expanded field of view also meant the weapons could track targets until the final seconds before impact, following laser designation adjustments throughout the entire flight profile. The guidance computer shifted from analog to digital processing using integrated circuits that TI manufactured for the commercial electronics market. Digital logic could process seeker input 20 times per second instead of the analog system's continuous but slow response. The faster update rate allowed more aggressive maneuvering during terminal guidance. Bombs could make sharper turns, compensate for crosswinds more effectively, and track moving targets if necessary. The digital computer also included built-in diagnostics that detected seeker failures or loss of laser signal, information that could be transmitted to ground crews through post-flight bomb inspection. Canard fin design changed completely. The original 4-fin configuration was replaced with a 4-petal airfoil that looked like a flower opening at the bomb's nose. Each petal could deflect independently through 20 degrees of travel, controlled by electromechanical actuators, powered by a thermal battery that activated when the bomb released from the aircraft. The new fins generated more control force at lower airspeeds, giving the bombs maneuverability throughout their entire flight envelope from supersonic release velocities down to subsonic terminal impact speeds. Paveway 2 also introduced different bomb body options. The original system worked only with 750-pound M117 bombs. The new version accepted M117s, 2,000-pound M118s, and even 500-pound Mk82 bombs for smaller targets. Each bomb size required different guidance kit components. The seeker head stayed the same, but fin size, actuator power, and control algorithms varied based on bomb weight and aerodynamic characteristics. TI developed a modular kit system where munitions crews could select the appropriate guidance package for the mission's specific target and tactical requirements. The laser designator systems evolved in parallel. Pave knife pods gave way to Pave tack, a stabilized turret that could be mounted under the aircraft's centerline rather than on a wing pylon. Pave tack included an infrared camera alongside the visible light television, allowing target designation through haze and battlefield smoke. The laser itself switched to a higher pulse rate, 20 pulses per second instead of 10, creating a stronger signal for the seeker to track. Later versions added coded pulse patterns that allowed multiple designators to operate simultaneously without interfering with each other, meaning several aircraft could strike different targets in the same area using laser-guided weapons. By 1975, Paveway 2 had replaced the original system entirely. The newer weapons achieved 48% direct hit rates in combat operations, measured as impacts within 10 feet of the laser spot, compared to roughly 5% hit probability for unguided bombs dropped from the same altitudes. That tenfold improvement in accuracy translated directly to mission effectiveness. Targets that previously required 20 sorties could be destroyed in a single pass with 4 laser-guided bombs. The strategic implications were enormous. The Pentagon's own analysis couldn't ignore the numbers. Between 1968 and 1973, the Air Force dropped 28,000 laser-guided bombs in Southeast Asia, achieving documented destruction of 20,000 individual targets, bridges, bunkers, command posts, radar sites, power plants, and ammunition storage facilities. The weapons destroyed targets on the first strike 73% of the time, compared to 5% single-strike success rates for unguided bombs. But the real transformation showed up in the cost analysis that Robert McNamara's systems analysts had pioneered years earlier. A single F-4 Phantom carrying 4 Paveway 2 bombs could destroy a hardened target with 90% probability. Achieving the same destruction probability with unguided weapons required an average of 18 sorties, 72 bombs expended, 18 aircraft exposure periods to defensive fire, and cumulative pilot risk that multiplied with each mission. The laser-guided bombs cost $3,000 per guidance kit in 1972 dollars. The unguided approach didn't just risk more aircraft, it consumed more fuel, more maintenance hours, more ordnance, and more time. The cost per destroyed target dropped from roughly $150,000 using conventional bombing to $12,000 using precision weapons, a 12-fold improvement in resource efficiency. Pilot survival rates changed even more dramatically. During Rolling Thunder operations from 1965 to 1968, the Air Force lost 382 aircraft to enemy action while attacking defended targets in North Vietnam. During linebacker operations in 1972, using laser-guided weapons as the primary strike tool, the Air Force lost 44 aircraft over 6 months of intensive bombing, roughly 1/10 the loss rate per sortie, despite hitting more heavily defended targets around Hanoi and Haiphong. The difference was exposure time. Precision weapons allowed single-pass strikes from medium altitude, minimizing time in the engagement envelope of anti-aircraft guns and surface-to-air missiles. The institutional resistance that Word had fought since 1965 collapsed once combat results became undeniable. Wing commanders who dismissed precision weapons as technical novelties started requesting maximum allocations of laser-guided bombs for their units. Strategic Air Command, the organization most committed to area bombing doctrine, began studying how to mount laser designators on B-52s for precision strikes against individual buildings rather than carpet bombing entire complexes. The Air Force's Armament Development Center at Eglin, which had rejected Word's initial proposal, established a permanent laser-guided weapons division and allocated $50 million for developing next-generation systems. Word received the Air Force Exceptional Civilian Service Award in 1973, the Pentagon's highest civilian honor, for developing a weapon system that had fundamentally altered air combat doctrine. The citation noted that his laser-guided bomb had saved hundreds of American lives by reducing required sorties against defended targets. But Word knew the real validation wasn't the award ceremony or the citation text. It was watching reconnaissance imagery from Vietnam, showing bridges destroyed, power plants collapsed, and command bunkers demolished, all with single strikes, using weapons his colleagues had told him the military would never buy. The skeptics who'd questioned operational practicality went silent after Thanh Hoa Bridge. The generals who wanted tonnage instead of precision started requesting briefings on how to expand laser-guided weapon production. The procurement officers who'd rejected his proposals in 1965 and 1966 were now processing contracts worth $200 million for Paveway 2 manufacturing. The Air Force ordered 80,000 guidance kits by 1975, enough to convert every general-purpose bomb in the inventory if necessary. Word's basement project had become the most successful precision weapon system in American military history. And it happened because one engineer refused to accept that bombing had to be wasteful to be effective. The institution eventually changed its mind because Word never changed his. Weldon Word retired from Texas Instruments in 1982, but Paveway didn't retire with him. The laser-guided bomb system he developed in a Dallas basement became the foundation for every precision weapon that followed. The Gulf War in 1991 showcased the complete transformation. American aircraft destroyed 90% of Iraqi command centers, 80% of strategic bridges, and 75% of hardened aircraft shelters using weapons that trace their lineage directly to Word's 4-quadrant photo detector and canard fin design. CNN broadcast footage of bombs entering building ventilation shafts and descending elevator shafts, strikes so precise they seemed impossible to audiences who remembered Vietnam-era bombing. The technology evolved far beyond Word's original analog circuits. Paveway 3 introduced inertial guidance combined with laser tracking, allowing bombs to navigate toward predicted target locations even when clouds temporarily blocked laser designation. GPS-guided joint direct attack munitions used satellite navigation instead of lasers, eliminating the need for designator aircraft entirely. But the operational concept remained unchanged: precision weapons that destroyed targets with single strikes, minimizing collateral damage and pilot exposure. Word's insight that accuracy mattered more than tonnage had become fundamental doctrine. The production numbers tell the adoption story. Between 1968 and 2025, the United States manufactured more than 500,000 Paveway guidance kits across 3 generations of design improvements. The weapons were exported to 38 countries, becoming the standard precision weapon for NATO and allied air forces. Israel used Paveway bombs to destroy Iraq's Osirak nuclear reactor in 1981, with 8 aircraft achieving what would have required hundreds of bombers using unguided weapons. British Tornadoes dropped Paveway bombs during the Gulf War. French Rafales used them in Libya. The weapon that the Pentagon rejected in 1965 became the most widely deployed precision munition in military history. Word's design philosophy influenced weapon development beyond laser guidance. The principle of modular kits that converted existing munitions into smart weapons became standard practice. GPS guidance kits for artillery shells, infrared seekers for anti-tank missiles, terminal radar homing for anti-ship weapons. The Department of Defense realized that upgrading existing inventories was faster and cheaper than designing entirely new weapons. Word had proven this approach worked when he bolted guidance kits onto standard M117 bombs rather than proposing a completely new munition. The strategic implications reached beyond military operations. Precision weapons changed what was politically acceptable in warfare. Governments could authorize strikes against leadership targets in urban areas because collateral damage could be minimized to single buildings. International law evolved to require precision weapons when available, making unguided bombing legally questionable, except against area targets with no civilian presence. The technology that Word developed to save pilot lives also made warfare more discriminate, though whether that encouraged or discouraged conflict remained debatable. Word died in 2006 at age 84, having witnessed precision weapons become so routine that their revolutionary origins were forgotten. Modern pilots trained exclusively on GPS-guided bombs often didn't know that laser-guided weapons predated satellite navigation by 2 decades, or that both technologies emerged from one engineer's determination to solve a problem that institutions claimed was unsolvable. The Dragon's Jaw Bridge, rebuilt after the war ended, stands as a tourist attraction now, a memorial to the 11 American airmen who died attacking it with unguided bombs before Word's technology made such losses obsolete. His legacy isn't just the weapons themselves, but the proof that precision matters. The Pentagon's 1965 rejection letter sits in the National Air and Force Museum in Dayton, Ohio, displayed next to a Paveway guidance kit as a reminder that breakthrough innovations often come from individuals willing to build prototypes in basement laboratories while institutions debate whether innovation is necessary. Word built it first, proved it worked, then let results change minds.